As promised, here are your next set of questions. 1. Calculate the pH of a 0.1 molar solution of nitric acid. 2. Calculate the pH of a 0.02 molar solution of potassium hydroxide. And finally, calculate the pH of a 0.003 molar solution of strontium hydroxide. Think you can do it? Let's find out. Number 1, 0.1 molar nitric acid. Guess what that means? 0.1 molar hydrogen ion. That easy. Take the negative log of that. We got a pH of 1. Number 1, because we're the best. Not 2, 1. All right, 0.02 KOH. That equals 0.02 hydroxide. POH equals the negative log of that, which is 1.70. But, Lenny, we don't want to know the pH. We want to know the pH. That's okay, because we got an equation for that. pH equals 14 minus our POH. So guess what we got? A pH of 12.3. It's basic, and that makes sense because this is the base. Your answers should always make sense. If it don't make dollars, it don't make sense. Now, number 3, 0.003 strontium hydroxide. Uh-oh, we got a 2 there. It means you got to multiply it by 2. So this will give us a 0.006 hydroxide ion. Take the POH of that, 2.22. pH, 14 minus 2.22, 11.78. How'd you do? Did you get 100%? You should have. This is pretty easy. Okay. The next thing we're going to talk about are weak acids and bases. They're all shriveled, atrophied. They're not strong. They're weak. Okay? Now the general structure, the way you write these reactions, HA, the proton, the acidic proton, and the acid. Now if you notice, I have a double arrow reaction. That's because these do not go to completion. They reach an equilibrium, which you should have learned in the last section about equilibrium. If you would like a refresher on that, feel free to click the link here. Okay, now, just like equilibriums, we have products over reactants. Products over reactants. Now for a base, we can have base plus water equals our hydrogenated base plus hydroxide. Again, products over reactants. Only this time, it's KB. What do you think that B stands for? Base. What do you think that A stands for? Acid. It's simply the equilibrium constant of our acid or our base. Products over reactants equal KB. Now with this information, we can figure out what our pH is by knowing how much we started with and what the Ka or Kb is. It's going to take a little bit of math, but it's going to be super fun. All right. Well, here it is. I promised you a question. This is it. This is the final question. I'm so excited. Now, calculate the pH of a 0.015 molar acidic acid solution. And then we'll get back together and compare our answers. It'll be awesome. Do it. Okay, here it is, our final solution. Now, because this was not a strong acid, this is a weak acid, I had to write out the reaction and figure out what I started with and what I ended up with. You know what that means? Are you guys ready for some ice tables? It's gonna be icy. Ice table? That's right. We're gonna make ice tables. Initial, change, and equilibrium. Now in the question, we started off with 0.015 acidic acid, which I showed here as a generic weak acid. Which means initially we had 0 hydrogen ion and 0 conjugate base. Now what was our change? We don't know. Minus X, plus X, and plus X. So, what's our equilibrium? minus x, x, and x. Now, how does this help us? What does it mean for this? Well, if we go back to our acid dissociation constant, we know that products over reactants equal our Ka. Therefore, the concentration of this times this divided by this will equal our Ka. Now, in the question, we were given our Ka as 1.8 times 10 to the negative 5. So this will equal x squared, because x times x squared, divided by our original acid, 0.015 minus x. But if you remember back to the equilibriums, we're going to have to do a quadratic equation here. Do you want to do one? I don't want to do one. So, a little trick we can do, take your initial concentration and divide it by your Ka. If that value is bigger than 500, we can ignore this minus x, and that makes it so much easier. I mean, unless you're in like quant or something where they're super picky, but that class is kind of dumb. So, having it like this, we can simply multiply each side by this, and then take the square root, and I'll solve for x. After doing that, I got x equals 5.20 times 10 to the negative 4th. Well, this is our x value. Guess what that means? It's also our hydrogen ion concentration. pH is the negative log of our hydrogen ion concentration, which we found to be this. So the negative log of 5.20 times 10 to the negative 4th is a pH of 3.28. Now that makes sense because this is acidic, and again, it was an acid. We made it, guys. We made it! Oh. So what did we learn today? Recap. We learned what is an acid and a base. What is it? Well, an acid makes the hydrogen ion concentration go up. The base either makes the hydroxide ion concentration go up or lowers the hydrogen ion concentration. Donates a proton, accepts a proton. Conjugates. What are conjugates? Conjugates are simply the same species on two sides of the reaction separated by one proton. Acidic acid, acetate. Water, hydroxide. Conjugates. pH of a strong acid and a strong base. Well, that's easy. Whatever your concentration is of acid, that's your concentration of hydroxide ion. Take the negative pH, bingo. Strong base, that equals your hydroxide ion. You know, multiplied by how many were in the original base. Could be 1, could be 2. Take the negative pH of that, that's your POH, minus it from 14, bingo. And a weak acid base, that's when we get to do our ice tables, and those are so much fun. Set up your acid or base dissociation constant, solve for x, negative log, bingo. Finally, yay.